So Unit 3 is discussing various polynomial functions and the different attributes of those functions. There's a lot in this unit, so make sure you study this for quite a bit before you take your exam. In section 6.3, we're just simplifying polynomial expressions, and it would be best if you could write your answers in standard form. So I notice we're adding these two polynomials together. So I'm going to look for like terms that I can add together. That gives me a 13x to the fourth. There's no cubic term, but I do notice there's one quadratic term. I'm just going to write him down. And then I see a plus 7x plus negative 6x would be a 1x. And then positive 2 plus negative 9 would be a negative 7. So that's my answer for part A. And then for part B, I notice we are subtracting our like terms. So 15x to the third minus 4x to the third is 11x to the third. No quadratic term, but negative 8x minus negative 7x is negative 8 plus 7, so that's a negative 1x. And then negative 11 minus 2 is a negative 13. For number 2, we're going to evaluate the function. You could either just on your calculator substitute in a negative 4 for all your x's. Just be careful that you use parentheses. The other option is you can store it on your calculator by first typing in negative 4 and then hitting the STO button above the on button and then typing in x, and then you'll just be able to type in the original expression exactly how it looks on your paper. So when you do that, either way, you get a negative 528 on your calculator. Then number 3, NHS is selling scarves for a fundraiser. The revenue is given by this equation. That's revenue coming into the fundraiser. And then the cost of creating the scarves is given by this function. When they ask what are the scarves selling for, they're asking about how much money they are selling for, not the purpose of the selling, which is a little misconception on the last quiz. So revenue is what we're taking out of the customer's hand. So it looks like we're selling the scarves for $16 each. The profit function can be found by taking your revenue and then subtracting off the cost, because cost is going to be removed from our profit. So for us, the revenue function is a 16x, and then when I subtract the cost function, which has to be in parentheses, so I remember to subtract both parts, that will distribute the negative, and we will get, let's see, that's 11.5x, and then a minus 120. So my profit function is 11.5 or $11.50 for each scarf minus $120 for setup. Find the profit of creating 60 scarves. I'm just going to put a 60 into this equation, and when I do that on my calculator, I get $570. So this next section has us do various function operations, and they define the functions up at the top of the problem. Here's f and here's g. So first they want you to just add the functions together. I know this notation confuses some of you. It's the same thing as saying f of x plus g of x. It's just a little bit fancy for the notation. So if I was to add my two functions together, I need to combine like terms. So I have 4x squared, 2x plus another x will be a plus 3x, and then negative 3 plus 1 will be a minus 2. And then it does say to identify any domain restrictions. This is a polynomial, so there are no domain restrictions. If you want to go ahead and list out the domain, it's negative infinity to infinity. The only one that's going to have a domain restriction is this problem right here. Number 5, we're going to multiply the polys together, and you can do this in any order, it doesn't matter, but what's so crucial is that you remember polynomials, when you're multiplying, are really gigantic distribution or FOIL problems. So you need to put them in parentheses so that everybody gets multiplied by everybody. So I'm going to kind of FOIL this or distribute this backwards. That'll give me a 4x to the third plus 2x squared minus 3x. And then I'm going to do the same thing with the positive 1. Oop. So let's see, that's going to be a plus 4x squared plus 2x and a minus 3. And when I add those together, I get my new polynomial, which is right there. Again, it's a poly, so there's no domain restriction, so the domain is negative infinity to infinity if you wanted to write it. Now number 6 is composition. It's fog, f of g of negative 5. If you prefer this notation, go ahead and write it this way instead. And the key to evaluating functions at numbers is you must start on the inside. So let's first start by finding g of negative 5. So if I go up to g and I plug in a negative 5, I get negative 5 plus 1, which is a negative 4. So now we're going to take f, and instead of evaluating him at negative 5, we're going to evaluate him at g of negative 5, which happened to be the number negative 4. And if I go back up to my g function here and I use a parentheses when I plug in a negative 4, I believe I get a 53. And this is my actual answer right here. The first answer I get is inconsequential to my final answer. Important to find it, but not important for my final answer. Number 7, f divided by g. You simply write them exactly how they appear. F divided by g. Whoops, that's supposed to be a negative. And then x plus 1. And then there is a domain restriction because my denominator can never equal 0. That means my x value cannot equal a negative 1 because that would produce a 0 in the denominator. Number 8, we want function f minus function g both evaluated at the number 8. So this is not composition, this is just subtraction, but we are evaluating at a number. I find it easier if I do f of 8 and then g of 8, and then I go ahead and subtract them when I'm done. So when I evaluate f of 8, I get 184. And when I evaluate g of 8, I get a 1. And then f minus the g gives me 183. Next section gives you two new functions, p and q. And I like this problem because some of you are still confusing multiplication with composition, and here you can see two very different problems side by side so you can understand the difference. Number 9 is a multiplication problem. So if you find p of 3, and then you can find q of 3, and once you get your answers you will multiply them together, that'll be your final answer. So p of 3, let's see, that gives me absolute value of negative 1, which is 1, 1 times 2 is 2, and then q of 3 is 4. And then final answer is when I take p of 3 times q of 3. So the final answer to this question is the number 8. This is very different when you look at number 10. Q of p of negative 4 is composition. You're going to use one function and then find the answer and plug that into the next function. So I'm going to start on the inside always when it's the composition of a number. Find p of negative 4. So let's see, that's 2 times negative 4 minus 4 absolute value. Absolute value of 8 times 2 is 16. And then we're going to take that number, 16, and plug that into q. And that's how we get our final answer of negative 9. The next section is 7.4, which is finding inverses. Remember, f of x is just function notation. It really just means y, and the first step in finding the inverses is to go ahead and switch where the x and y are located in the problem. Now, as always, you need your functions to be in y equals form, so if I needed to solve for y, I could simply multiply by the reciprocal on both sides. And I'm going to flip this around real quick. It's y equals negative 3 over 2x. But to be exactly wonderful, I would like your answer in function notation for inverse, which is f to the negative 1 of x instead of y. Because that way you can signify for your reader, here's my function's inverse, as opposed to just putting a y down. That gets a little confusing. Number 12, same thing. F of x is just fancy function notation for y. So my first step in inverse functions is switching the x and y. And now I need to do some work to isolate the y value. So I'm going to start by adding the 14. And then I have a fraction coefficient, so I'm going to multiply by the reciprocal. To everybody, notice the parentheses, please. And I'm going to flip this around, and when I go ahead and distribute the 2/7, I get 2/7 x plus, so it's a 4. And then my final exact wonderful answer would be f to the negative 1 of x equals 2/7 x plus 4. Alright. I want you to graph two examples of functions whose inverses are also functions. So there's a lot of different answers you can give me, but because I want my originals to be functions, that means they have to pass the vertical line test. And then because I want my inverses to be functions, that also means the originals have to pass the horizontal line test. So you could just draw a straight linear equation function that definitely passes the vertical and the horizontal line test. You could get a little fancy and draw like a cubic that looks like this. And I kind of made it seem like it went flat, but it doesn't. But it does pass the vertical and the horizontal line test. And the reasons explain why. The original is a function if it passes the vertical line test, and the inverse is a function if, and this is the important part, if the original passes the horizontal line test. And I think last time on your quiz some of you weren't specific enough about saying who has to pass what test. Number 14, you need to have your factoring flowchart out, and your factoring flowchart says the first step in every factoring problem is to factor out any common terms. So when I look at number 14, I notice there's a common 8 that I need to take out. And when you take out that common 8, then you should notice you have the sum of cubes pattern right here. So the A value is x, and the B value is 3. I found those by cube rooting both of these. The 8 stays in front, and then I just follow the pattern that's on your flowchart. You don't have to have it memorized, so I expect these to be really great questions for you all. Okay, number 15. There's no common term, but I do notice that both of these are perfect squares. So if I go ahead and square root both of these, so that means the A is going to be a, let's see, 4x squared, and the B is going to be a 7y. And I plug that into the A plus BA minus B pattern. Any order does not matter. And you do have to be a little cautious that there's not a difference of perfect squares that pops up again. For instance, this part, it is a difference. The first one's a perfect square, but the second one's not. So this is actually the final answer to that factoring question. Number 16 is 4 terms, which means we're going to factor it by grouping. So I'm going to start with the first group. And when I take out my common term of x squared, I'm left with 2x plus 3. And then for my second group, I'm going to take out a common factor of -1, so I can switch all the signs to 2x plus 3. Then you should notice that what's in the parentheses matches. We're going to take that all the way out of the problem. When I remove the 2x plus 3's, I'm still left with x squared minus 1. Now, unfortunately, we're not done, because x squared minus 1 is another difference of 2 squares. So 2x plus 3 will stay, but x squared minus 1 is really x plus 1 times an x minus 1. And that is the final answer I need to see. 17 is 4 terms again, so we're going to factor by grouping. I notice there's an x squared right here. So that leaves me with 5x minus 1. And then there's nothing in common to factor out of the second group, but I do need to factor something out. So I'm going to go ahead and take out a positive 1, because that won't affect what's in the parentheses, because I don't want that to change, but I do need something to come out. So the common 5x minus 1 will now come out in front of the whole problem, and we are left with x squared plus 1. Now there is no way, without using eyes, to factor a sum of perfect squares, so that is your final answer. Number 18, no common factor, but it is a trinomial, so we're just going to think about backwards FOILing and how we would get this trinomial if we backwards FOILed. So I see an x squared and x squared is the only way to get an x to the 4th, and then multiplies to 27, adds up to -12. There are a few options, but I'm thinking a -9 and a -3. Unfortunately, this guy right here is the difference of 2 squares, so we're still not done. He's going to become an x plus 3, x minus 3. And then the x squared minus 3 can stay, because he is the difference, but they're not both perfect squares, so I don't need to factor that any further. Oh, 19's a mess. There's a common factor of 3, and then also x to the 3rd. So let's take that out first. And once you take out those common factors, it usually frees up your problem, so you don't have to think too hard. Plus 12. Now what's left in the parentheses is just a basic trinomial. We should be able to factor that pretty quickly. I'm thinking x minus 6, x minus 2, with the 3x to the 3rd out in front. That does not move. And then number 20, there's no common factor, but I do notice that these are both perfect cubes if I look at the list. So when I cube root both of them, I get a is 2x, and then I get b of 5. The negative is already built into the formula. So following my cubic formula, which says a minus b, a squared plus ab plus b squared, I would do 2x minus 5. And then this is the part I'm a little nervous about. A squared, if you square 2x, you get a 4x squared. And then a times b is plus 10x, b squared is plus 25. Cubic patterns will never factor any further than that, so once you pull out a cubic pattern, you should be done with the question. How will you identify if an expression is a factor of a polynomial? So my hint to you is see synthetic division or when we did polynomial graphing. Two ways. You could, if you divide synthetically or normally even, if the remainder equals 0, then it is a factor. Or, and I like this one a lot better, if we'll just say the graph has an x-intercept at the solution to the factor. So as an example, if you had a polynomial that kind of looked like this, and you saw right here that he had an x-intercept at, let's say that was -3, that meant that x plus 3 would be a factor of that particular polynomial. Okay, 22. If 5i is a 0 of some mystery polynomial, what else do you know? Well, I know that complex numbers come in complex conjugate pairs. So if 5i is a 0, his complex conjugate pair would also be, would be the -5i. Easy as that. All right, we're going to divide these two polynomials now. It doesn't tell us how, so I would kind of vote for synthetic division because I like it a lot better. If x minus 3 is the divisor, then the thing that goes in the box is the solution to that, which is a 3. And then we're going to line up our coefficients, but I need you to be really careful because this particular poly goes from cubic and then skips over the quadratic. So you need to put a 2 coefficient and then a 0 because there's no quadratic, -4, and a 5. And trust me when I tell you there is something similar going to happen on your test where you do have to watch for placeholders. So you bring down the first coefficient, and then it's a series of multiplies and adds. Synthetic is significantly easier than long division because most of you like to multiply and add over subtract and divide. So add, 6 times 3 is 18, add is 14. Where are we at? Let's see. I did something wrong. Oh, no I didn't. Never mind. 42. Add that together and you get a 47. Now, they never told us that this would divide pretty, and we do indeed have a remainder. This is our remainder right here. But we're still not done because I need you to write your answer in proper notation. We had a cubic divided by a linear, which means we brought this down to a quadratic. So it's 2x squared plus 6x plus 14. And then a remainder of 47 is still being divided by the x minus 3. He's still in process of division. So that is my final answer. And if you chose to do long division, good for you. It's still going to come out to the same answer. All right, this guy needs some calculator help. So, well, before I grab the calculator, I do notice a few things. I am going to have an x-intercept at -4, and then x minus 1 squared means this answer shows up twice, so it's going to bounce at x equals 1. So there's a bounce right here and an actual crossing right here. Unfortunately, that's not enough information, so I do need to get this typed in my calculator because I'm feeling we have a max or a min that we need to graph as well. So x plus, whoops, not what I wanted to do. X plus 4 x subtract 1 squared. Sorry, I'm sick again. What's new? Ooh. Unfortunately, I think the graph I gave you doesn't do a real great job. Even on the standard window, it's not high enough, so I'm going to change this to go up to 20 for the y's. And I'm going to go ahead and find this maximum. I think I already know this minimum because we discussed that it was going to bounce off at x equals 1, and that is indeed the place where it bounces. So using my calculus menu, I'm going to find that relative maximum over here. So it says go to the left. Sure. Go to the right. Sure. And guess. And we got a max at roughly negative 2.3, 18.5. So a little bit of a bummer here. I'm not going to be able to, I'm not going to be able to graph this real well because the max is way up here. So just do the best you can. If something like this were to happen, oh geez, on the actual, oh gosh, that's even worse. You get the idea. On the test itself, I hope it doesn't, but if it does, just do the best you can. So 25, they say specifically to use synthetic division, so I will do as I am told. And I'm going to put the solution to the divisor right here, so that's a 4. And then again, cubic, quadratic, there's a missing linear term, so a 0 followed by a 2. And they didn't promise me that this would come out pretty, so we're just going to divide. Okay, 4 times 4 is 16, plus negative 10 is 6. That's a 24. It's a 24. And then, let's see, it's a 96, which gives me a 98 remainder. Remember, he's your remainder. So our final answer was a cubic taken down one level, so now it's a quadratic, 4x squared, plus 6x, I think that says plus 24, and then a remainder of 98, who's still in the process of being divided by the x minus 4. Now this next question does say use long division. You must use long division. I know you don't like it, but you have to use long division. So I'm going to try to color code this so you can follow it a little easier. We're going to start with dividing this first term by this lead term. 6x to the third divided by 2x would give me a 3x squared. Okay, the next step is to multiply. Remember that 3x squared is going to get multiplied by everybody here. So that gives me a 6x to the third and then a minus 3x squared. The next step in long division is to subtract. The first term should always cancel out. 7 minus negative 3 is really 7 plus 3, so it's 10x squared. And then bring down the next term. And now we repeat the process. So 10x squared, divided by 2x would leave me with 5x. Now we multiply 10x squared minus 5x. Now we subtract. That lead term does cancel out. Careful, I have negative x minus a negative 5x. Negative 1 plus 5 is what we have. So that gives us a 4x. The most common mistake on long division is not the division itself or the process, it's the subtraction. So now I take the 4x and divide it by 2x, and I like to write it off to the side because I tend to make silly mistakes if I don't. That gives me a positive 2. Now we're going to multiply, and that gives me a 4x minus 2. Oh, that's cool. I think we're going to have something awesome happen. When I subtract, these end up canceling, and negative 2 minus negative 2 also cancels. I have no remainder. So the final answer to this question is 3x squared plus 5x plus 2. Neat. Alright, this next guy. Find all roots. Roots, by the way, are the same things as zeros. So at the end of our question, we're going to have like x equals, and because it's a cubic, technically we're going to have 3 answers, but it's going to be kind of odd at the end of this question. Odd meaning weird, not odd versus even. So we're going to graph this on our calculator and find a rational root, which means when I look on my calculator, I'm going to see that when I type this into y equals, not this part, this guy seems to have an x-intercept at negative 3. So I don't know exactly what he looks like, but something like this. So negative 3 is going to be a good starting point for us. Then it leads you through the question. It says, now do synthetic division. You put the actual intercept or the root in the box, followed by the coefficients. And then because we know this is a root, we better come up with a remainder of 0. That's the whole purpose of this, because we need to bring it down to a quadratic level. Multiply and add. Oh, cool. I think it's going to work. Yep. Sure enough, I do get a remainder of 0. Now notice the directions say, now write your polynomial as a product of a linear and quadratic factor. What we have here is x minus 3 is a root. That means x plus 3 is the factor. And then if I take this thing that's in red right here and write it as this polynomial as quadratic, I get x squared plus 4x plus 7. They still want us to find all of the roots, and I already found one through inspection of the graph, but now part C says use quadratic formula to find the remaining roots. The reason we have to use quadratic formula is because x squared plus 4x plus 7 is not factorable, and I guess the only other option is you could complete the square instead of using quadratic formula, so if you really wanted to do that, you go right ahead. I'm going to use quadratic formula, so it's negative b plus or minus square root of b squared minus 4ac all over 2a. So negative b plus or minus square root, b squared is a 16 minus 4 times a times c all over 2 times a. So let's see, I think it gives me a negative 12 in the square root. Ooh, no wonder we couldn't find anything. This is going to have i's in it. So we have negative 4 plus and minus. If I break down negative 12, it's 4 times negative 1 times 3. So that gives me plus and minus 2i squared to 3 all over 2. And then remember, everything here has to be divided by the 2. So I end up with negative 2 plus and minus 1i squared to 3. So this technically is my other two answers. It's a negative 2 plus I squared to 3 and a negative 2 minus I squared to 3. Pretty gross. Ugh. You need to know quadratic formula. It will not be given to you. Okay, 28. State the number of complex solutions. Remember in the last example, we were able to graph the function and see that there was one place where it definitely crossed, well, this isn't it, but one place where it crossed the x-axis very clearly, which meant that any other solutions we had would have to be complex or imaginary, and that's what we saw in that last example. So let's go ahead and type this one in and take a look. Whoops. Apparently I'm still asleep. Ugh. And then I'm going to subtract 8x and add 37. Hi, I'm recording. So I'm going to, okay. I can't really see what's happening, so I'm going to zoom out. Whoops. And when I zoom out, I notice that this function crosses the x-axis twice. So since we have, oops, let me get this out of here. Oh, no, cancel. My polynomial was a quartic, a degree 4, which means it's supposed to have a total of 4 solutions. Well, if 2 are real, and I'm supposed to have 4 solutions, that must mean that 2 are imaginary, or else some people call them complex. So that's what my answer is. If I can't see the intersection of the x-axis, or at least a bounce off the x-axis, that means the rest of the solutions must be complex. Oh, this next question, find all the zeros. A lot of ways we could do it, but if you're lazy like me, you're just going to check your calculator first. When I check my calculator, what I mean by that is typing it into y equals and graphing. And then I'm going to go back to the standard window because I can't really see what's happening right now. I think these are probably nice. Oh yeah. So I can see very clearly that this function has a solution at -1, 3, and 5. And I'm going to write that down. So -1, 3, and 5. And that's as simple as you can do. Write an equation with the least coefficient that has these zeros. Now if these are the zeros, what that means is for my polynomial, which you can call f of x, p of x, q of x, I don't care. The factor would be x minus 4 if the solution is x equals 4, and then x plus 2, and then x minus 5. Morning. And then we need to simplify this by foiling it out. So I'm going to go ahead and FOIL the back 2. Whoops. It says minus 4. So if I FOIL this together, I get x squared minus 3x minus 10. And then when I distribute the x, because I got to FOIL it all the way out, I get x to the third minus 3x squared minus 10x. And now we're going to distribute the -4. So we have a -4x squared plus 12x plus 40. And then almost done. Final answer for my function is x to the third minus 7x squared plus 2x plus 40. All right. I do need you to expand out the answer. This next problem is all on the calculator. So, well, I shouldn't say that. The first two questions are not. The degree is the highest exponent, it's 4, and the lead coefficient is the coefficient in front of the lead term when it's in standard form. So there's an invisible 1 as a lead coefficient on that particular question. Now we have to go to our calculator. I can find them. And in y equals, I'm going to type this new function, which was x to the fourth plus 8x to the third plus 3x squared minus 20x. And I know some of you at home might not have a graphing calculator, so you might be having to use one on a computer, or you're just watching this to kind of get a feel for it. That's okay. Standard window to start. Alright, bit of a bummer because there are 1, 2, 3, 4 x-intercepts. And another problem is I don't think we can see this relative minimum that's over here, and there's also a relative max up here. So I'm going to expand my y's so they're a little bigger. -20 to 20 should do it, but let's, whoops. No, oh man. Let's try that again. Clear. Try this. There we go. So when we graph this, oh, still not big enough. Go back to my window and let's take the y minimum to be safe and say -40. Alright, so still not low enough. Alright, let's try again. We need to go maybe to -60. That better be low enough. Oh my goodness. Okay, one more. Definitely not low enough. Okay, I'm going for broke here. -160. And now, I still can't see it. Alright, -200. Okay. So we're going to be able to find 4 x-intercepts. I'm just going to find one for you, and then I'm going to just tell you the other 3 because I just don't have time to do all that. So, oops, x-intercepts. When you find an x-intercept, you choose the 0 locator, the 0 finder. And it's a little difficult to see right now. I'm actually going to get out of this real quick. I'm going to expand my window up again so that way it goes higher because I just can't see enough. Alright, now I'm going to go ahead and use my calculator to find one of the x-intercepts. So it says go left bound, so I'm going to find this x-intercept right here. I'm going to go a little bit to the left, and then a little bit to the right, which brings me above the x-axis, and then guess, hit enter one last time, and one of your zeros is negative 2.12. They're going to do that same process for all the other zeros, and I'm going to cheat through the magic of television. All the zeros, I'm just going to list them for you. Let's see, they were negative 7.20, it says it around there's hundredth, by the way, negative 2.12, there's a nice one at 0, and then 1.31. Now to find the maximum, remember you're going to use that same calc menu, but if they want the maximum, make sure you choose the maximum finder. I need the whole ordered pair, so that came out to negative 1.19 and then 16.57. And then the minimum, there was actually 2 for relative minimum. Negative 5.57, negative 1.19. And then there's also, let's see. Oh, no, that was not the right number. 215.45. Sorry, I was reading the wrong problem. And then there's one at 0.76, negative 9.62. And then the final couple questions ask about where the function was increasing and decreasing. And remember, these are domain intervals, so you should only be looking at the x values of the turning points. So x values of the max and min. So for the sake of time, I'm going to tell you the function is decreasing at 2 locations. The first interval is from negative 5.57 to negative 1.19. Union, the next time it's decreasing is from 0.76 to infinity. And then the intervals for where the function is increasing is from negative infinity to negative 5.57. And also from negative 1.19 to 0.76. Notice the only numbers that I listed besides the infinities were the x values of your max and your min. The end behavior always starts the same way. F of x approaches something as your x's go to the right, or left, let's do first. And then f of x approaches something else as your x's go to the right. So let's see, this guy looked, it was a quartic. The end behavior did a lot of stuff in the middle, but basically it went up on both sides. So as my function travels to the left, or my x's travel to the left, my function travels up. As my x's travel to the right, my function also travels up. And then the domain, because it's a normal polynomial, is always negative infinity to infinity. But the range, what you need to do is identify the lowest possible, because it's range, we need to identify the lowest y value. And remember, that was that negative 215 thing. So for us, the range is negative 215.45, and then it travels up to infinity forever. And that is your unit 3.